In this video, we'll learn how to use definite integrals to compute volumes of solids of revolution where the slices are not in the shape of disks or washers, but rather tubes. Here's the graph of a region. The top boundary is the function y equals the quantity 1 minus x times the quantity x minus 6, and the bottom of this region is the x-axis. In a previous video, we rotated this region about the x-axis, or about a line parallel to the x-axis, and we used cross-sections that took the form of disks or washers to find the volume of the region. But what if we rotate this region about the y-axis? What is the shape of the solid formed by doing so? We get an object that you might use to bake a certain type of cake called a bundt cake. But how would we find this volume? We would first take a slice of this region perpendicular to the x-axis or parallel to the y-axis and look at various representative slices between x equals 1 and x equals 6. When we rotate one of these slices about the y-axis, we get a shape that is not a disk or a washer, but which looks like a tube. Could we find the volume of this very thin tube, or sometimes it's called a cylindrical shell? As before, we sketch the region, we draw a representative slice, and we draw the tube that slice traces out as we rotate it about the y-axis. This tube has a height that is the same height as our slice, which in our case is the quantity 1 minus x times x minus 6. How could we find the volume of this very thin tube? If we were to cut the tube down the side and unroll it, we would get a rectangle. The height of this rectangle is still the quantity 1 minus x times quantity x minus 6, and the base of this rectangle would be the circumference of the tube. The radius of this tube is the distance from the y-axis to the slice, which we can simply call x, as x ranges from 1 to 6. So the circumference of the tube, or the base of this rectangle, would be 2 pi x. This slice, this rectangle, has a very thin width, delta x, which is the width of the slice. So if we form the volume of this little x slice, we get 2 pi x times the height of the slice times delta x. We can approximate the total volume of the object by summing up these x slices. And this Riemann sum converges to a definite integral, as we have seen many times now. The limits of integration here would be from 1 to 6, so that we get every possible slice in the region. Now we just need to work out the integral. And we get 875 pi over 6 for the volume of this three-dimensional solid. If instead of rotating about the y-axis, we had rotated about the line x equals 9, how would the setup of this integral change? We would still have a tube as we revolve this blue slice around the line x equals 9. The height would still be the same. The width of the slice would still be the same, but the radius of the tube would now be the distance from the line x equals 9 back to where we have this value x. So the radius would be 9 minus x. We still need the 2 pi here from the circumference of the tube, but the limits of integration would still be 1 to 6, so that we get every possible blue slice. I'll let you work this one out, but it's still the integral of a polynomial. In general, how do you know when to use the tube method versus the disk or washer method? Well, in all of these problems, you should draw a sketch of the region in the xy plane. Then draw a representative slice. In this case, we could have sliced things horizontally instead of vertically, but it would have been more difficult to solve for the equations of x in terms of y of the two branches of this parabola. So a vertical slice seems more reasonable. Once you have your slice, rotate it around your axis of revolution and determine whether you get a washer, a disk, or a tube, then set up the appropriate integral. Sometimes you might be able to set up both types of integrals, but one may be easier to work out than the other.